Hi everyone, my name is Ricardo Duran and I will be presenting the paper for Robo ADS, which stands for Anomaly Detection Against Sensor and Actuator Misbehaviors. And this study is done in mobile robots. Excuse me. Firstly, I would like to give credit to the authors that did this research, like Pinyao Guo, Honmin Kim, Nurali Birani, Jun Shu, Minghui Shu, and Peng Liu. So in recent years, we have seen that there's a very rapid growth in the robotics industry, and the prediction basically for the spending on robotics and related services will be it's estimated that it's going to be $188 billion by year 2020, which is basically next year. Also, major companies, tech companies like Google, Uber, and Tesla are leading intensive developments for autonomous driving, basically to replace human drivers in the very near future. And this entails that mobile robots play a major role here. And this is the reason why it's so important to prevent malfunctioning due to the robot misbehaviors. We'll see what misbehaviors are shortly. So first let's see about the robots and their vulnerabilities. So robots, unlike cyber systems like computers or mobile phones, the mobile robots are very strongly coupled to the cyberspace and the physical world in which they operate. So because of this, they depend almost entirely on their sensors and actuators, sensors such as global positioning system, accelerometer, and actuators such as the electrical control units. A variety of sources can threaten the operation of a mobile robot, and this will lead to the misbehaviors that we talked about before. Here are some reports that show how important it is to be very stringent about the safety of these robots. So in 2011, an American surveillance drone was brought down by Iranian cyber warfare through the use of GPS spoofing attacks. Also, Google reported in 2015 that 272 autonomous vehicles were having disengagements because of sensor or actuator communication failures. So speaking of the robot misbehaviors, an active misbehavior can be basically either a sensor misbehavior or an actuator misbehavior. Sensors we can see is GPS spoofing, alter authentic readings on a sensor received by the control units, and actuator misbehaviors, for example, is the steering wheel takeover or non-intended acceleration, for instance. These are some of the misbehaviors. Here we can further see that these, both the actuator and sensor, can be having misbehaviors through either physical or cyber channels. And this is very well represented in this picture over here. And in this table we can see, for instance, that GPS spoofing is indeed a sensor misbehavior that can be done through the physical channel. An unintended acceleration, on the other hand, is an actuator misbehavior that can happen through the cyber channel. So that brings us to the challenges to build an autonomous detection system for robots. So firstly, the robots are nonlinear systems, subject to stochastic noises in sensing and actuation. Both misbehaviors, either sensor or actuator, can be very disastrous for robots, and the defender has no knowledge of the sensor conditions. So, for example, which sensors are corrupted and which are clean. And lastly, there is already some anomaly detection systems that have been studied in recent years, but none of the existing approaches is capable of handling all the previously mentioned challenges, which is why Robot ADS research happened. Basically, the robot anomaly detection system is leveraging dynamic models and builds correlation between the potentially corrupted sensors and the control commands. So also the states, the intermediate states, and sensor readings are estimated. These discrepancies, the discrepancies found between the estimated values and the measured values indicate misbehaviors. So what anomaly detection system for mobile robots tries to contribute is a generalizable model-based anomaly detection system for sensor and actuator misbehaviors of nonlinear mobile robots, as well as a quantitative understanding of how the robot properties and anomaly detection system decision parameters affect the performance of the misbehavior detection in the real world robots. So this research has been implemented in a couple of robots to test its effectiveness and efficiency against various attacks. And both evaluations show less than 3% of false positive rate and less than 1% of false negative detection on average. The robot ADS basically is deployed in the planner of the robot, which basically is receiving sensor data and then executing control commands accordingly. We can see the sensing workflow goes in, and then the actuation workflow comes from the planner towards the actuators to execute commands. Then we can see that the robot anomaly detection system design consists of a monitor that is getting copies of the commands and the sensor readings, and this is fed to the multimode estimation engine, which has a lot of or different algorithms for the different modes, which are basically the NUISE, which stands for Nonlinear Unknown Input and State Estimation Algorithm. Then, depending on the mode that is been selected, this multimode estimation engine will feed the results to the decision maker, which uses chi-square to determine which sensors are estimated as corrupted. So we can further discuss this. Like I said, firstly, the monitor in each control iteration, the control unit sends a copy of the control commands of the monitor, and after these commands have been executed, the monitor collects the sensor readings of all these sensors, and then this is sent to the multimode estimation engine. The multimode estimation engine is basically the core of the Robo ADS, and the key insight is the following one. The control commands and sensor readings are correlated using robot states as intermediate. So executed control commands determine how the robot evolves from the initial state to the new state, and then the new state is captured by the sensor readings. So basically, This means that the sensor readings can be utilized to estimate new states, and that the executed control commands can be further estimated from the new states. Therefore, the discrepancy between the planned control commands and the executed control commands estimated by sensor readings can point out the existence of actuator misbehaviors. The goal of this multimode estimation engine is ultimately to obtain a minimum variance on bias estimates for sensor anomaly and actuator anomaly detection vectors. The mode selector basically compares the likelihood of each mode and then selects the mode with the highest likelihood to reflect the ground truth. The state estimates are updated for the next iteration, and the anomaly vector estimates of the selected mode will be leveraged for the decision-making process. This brings us to the decision makers, which, like I mentioned before, this conducts a chi-square test to check that the estimated sensor and actuator anomaly vectors are exceeding thresholds with a certain level of confidence. These results go through sliding windows to reduce transient faults, and the decision maker will raise an alarm from the detector only when a certain number of positives appear in consecutive iterations. So when this is detected continuously, then the decision maker raises an alarm to confirm misbehaving sensors, and the anomaly is split further into further chi-square tests conducted separately for each individual testing sensor. The decision maker analogously raises an actuator misbehavior alarm and calculates actuator anomaly vector estimates for each actuator. As it was mentioned previously, this has been implemented on 2 robots. We will discuss the Kefera robot. Basically consists of like 3 sensors. It has a LiDAR sensor, which is basically a laser sensor that determines the robot location. Then we have as well an indoor positioning sensor, and a wheel encoder. The decision parameters utilized for the robot are like window sizes, the detection criteria, and the detection confidence level. And the mission of the robot is basically to receive a map with information of the target location. Then the planner will calculate a collision-free path using a rapidly exploring random trees algorithm. And a PID closed loop will be used to control and track the planned path using real-time positioning data from the indoor positioning system. There was a series of attack and failure scenarios and detection performance that was learned from this implementation. Here we can highlight that on the scenarios number 9, 10, and 11, 2 out of the 3 sensors were actually detected corrupted, and they are different kinds of attacks. So for instance, first there's a denial of service and a wheel encoder logic bomb. Then this is the indoor positioning system spoofing and another denial of service on the LiDAR. Then repeating the logic bomb on the wheel encoder, but now together with the indoor positioning system. This brings us to the conclusion, basically, and the future work as well. So sensor and actuator misbehaviors impose very big threat in mobile robots. And in this study, it is proposed to have a practical robot anomaly detection system that is capable of detecting both type of misbehaviors in the real world robots, which are the sensor and the actuator misbehaviors. And this is in order to bridge the gap from a detection method to a practical system. The system implementations on the two robots have shed light on the application, and it confirms that the detection system has good effectiveness and small detection delays. So for forensic purposes, the future work will focus on further identifying the point of attack and failure once a misbehavior is detected in a workflow. This is the sensing workflow or actuator workflow. Designing computationally efficient response algorithms is also worth exploring. So this brings us to the end of the presentation. I hope you have enjoyed this presentation, and please provide your feedback in Piazza. Thanks.